Basic Vibration Analyst, Fundamentals of Signal Processing, Understanding Key Concepts Behind Vibration and Waveform Analysis. Overview and Importance of Vibration Analysis. Vibration analysis is a critical technique used in predictive maintenance and condition monitoring of rotating machinery. It helps identify mechanical issues such as imbalance, misalignment, bearing faults, and gear defects before they lead to catastrophic failures. Understanding vibration signals and their processing is essential for accurate diagnosis. This introduction will cover why vibration analysis matters, its role in reducing downtime, and how it contributes to cost savings and operational efficiency. By analyzing vibration patterns, engineers can detect anomalies early, plan maintenance schedules effectively, and extend equipment lifespan. The process involves capturing vibration data using sensors, converting it into meaningful information through signal processing, and interpreting the results to make informed decisions. This foundational knowledge sets the stage for deeper exploration into signal processing concepts, analyzer tools, and practical applications in industrial environments. Core principles and techniques. Signal processing in vibration analysis involves converting raw vibration data into a frequency domain representation using techniques like fast Fourier transform or FFT. This transformation allows analysts to identify specific frequency components associated with machine faults. Here's this diagram concept of frequency domain transformation for vibration analysis. Structure of left side diagram, a graph labeled as time domain, x-axis called time, in seconds, y-axis called vibration amplitude. It is show a raw vibration signal or irregular waveform. Structure of center side diagram, a block labeled FFT or fast Fourier transform, arrows pointing from time domain graph to FFT block. And structure of right side diagram, a graph labeled frequency domain, x-axis called frequency in hertz, y-axis called amplitude. It is show a distinct peaks at certain frequencies, representing machine fault frequencies. For annotations, convert raw vibration data into frequency spectrum, then identify fault frequencies accurately, such as bearing, gear mesh. Key principles include sampling rate, Nyquist frequency, and filtering to remove noise. Proper signal processing ensures accurate detection of fault signatures such as harmonics or sidebands. Analysts must understand how time domain signals translate into frequency spectra and how resolution impacts the clarity of fault identification. The sampling and filtering diagram with Nyquist frequency and aliasing risk concept. Please note for color coding, blue for raw signal, green for sampling points, and orange for filtered signal. Here's the explanation of structure of the diagrams. The left side diagram is a raw signal, a continuous waveform labeled analog vibration signal. It is annotated as real-world vibration data. The middle side diagram is a sampling. It shows discrete points taken from the analog signal. It is labeled as sampling rate or Fs. Note for takeaways is Nyquist frequency equals F sub s divided by 2, and the right side diagram is a filtering. There are two graphs. Before filtering is called signal with noise, and after filtering is called clean signal. It is labeled as apply low pass or band pass filter. Note for takeaways is remove high-frequency noise for clarity. Additionally, windowing techniques are applied to minimize spectral leakage, and averaging methods help reduce random noise. These concepts form the backbone of vibration analysis, enabling precise interpretation of machine health and facilitating predictive maintenance strategies. Here's the explanation of diagram layout of windowing and averaging for precise fault detection. Please note for color coding, blue for raw signal, green for windowing process and Hanning curve, and orange for averaged spectrum. The left side diagram is a raw FFT spectrum. It is show a spectral leakage or side lobes around peaks. It is labeled as without windowing, then leakage present. The middle side diagram is a windowing. It is display Hanning window shape or smooth curve tapering at ends. It is show time domain signal multiplied by the window. Arrow pointing to improved spectrum with reduced leakage. It is annotated as windowing reduces spectral leakage, and the right side diagram is an averaging. It is show multiple FFT spectra combined into one smooth averaged spectrum. It is labeled as averaging reduces random noise. It is annotated as improves clarity for fault detection. Analyzer components and functions. Modern vibration analyzers are equipped with advanced features to capture, process, and display vibration data. Key components include accelerometers for data acquisition, signal conditioning units, and digital processors for FFT analysis. The user interface typically displays time waveforms, spectra, and diagnostic tools. Understanding the layout and functionality of your analyzer is crucial for efficient operation. Analysts should familiarize themselves with menu navigation, parameter settings, and data storage options. Many analyzers also offer connectivity for remote monitoring and integration with maintenance management systems. A quick tour of the analyzer ensures users can configure measurement settings correctly, interpret graphical outputs, and utilize built-in diagnostic features effectively. This knowledge enhances accuracy and confidence in vibration analysis tasks. Understanding Fmax and resolution. Fmax, or maximum frequency, defines the upper limit of the frequency range displayed in a spectrum. Selecting an appropriate Fmax ensures that all relevant fault frequencies are captured without unnecessary data overload. Here's the definition of Fmax diagram. The left diagram is time domain signal converting into FFT process. The right diagram is frequency spectrum with Fmax marked and typical fault frequencies shown, imbalance at the low frequency, and gear mesh at the higher frequency. Fmax is the upper frequency limit in a vibration spectrum. It determines how far the FFT analysis will calculate frequency components. If Fmax is too low, you might miss critical fault frequencies, such as bearing defects. Gear mesh. If Fmax is too high, you capture unnecessary data, increasing processing time and reducing resolution. Lines of resolution, LR, determine the number of discrete frequency points within the selected range, impacting the clarity and detail of the spectrum. Higher resolution provides finer detail but requires longer acquisition time and more memory. Conversely, low resolution may obscure critical fault signatures. Analysts must balance Fmax and LR based on machine speed, fault frequencies, and diagnostic objectives. Incorrect settings can lead to missed faults or inefficient data collection. Understanding these parameters is essential for accurate and efficient vibration analysis. Purpose and techniques. Spectral averaging is a technique used to improve the signal-to-noise ratio in vibration analysis. By averaging multiple spectra, random noise is reduced, and consistent fault-related signals become more prominent. There are different types of averaging, including linear and exponential, each with specific applications. Linear averaging treats all samples equally, while exponential averaging gives more weight to recent data, making it suitable for trending. Averaging is particularly useful in environments with high background noise or fluctuating operating conditions. Proper application of spectral averaging enhances diagnostic accuracy, making it easier to identify subtle fault signatures such as bearing defects or gear wear. Analysts should understand when and how to apply averaging to optimize data quality without masking critical information. Impact on diagnostic accuracy. Choosing the correct Fmax and lines of resolution is vital for effective vibration analysis. An inappropriate Fmax may exclude critical fault frequencies, leading to incomplete diagnostics. Similarly, insufficient resolution can obscure fault signatures, while excessive resolution may result in unnecessary data complexity and longer processing times. The selection should consider machine operating speed, expected fault frequencies, and analysis objectives. For example, detecting bearing faults requires higher resolution to capture subtle frequency components, whereas imbalance detection may need a lower resolution. Incorrect settings can lead to misinterpretation, wasted resources, and potential equipment failure. Therefore, analysts must apply best practices and guidelines to ensure optimal parameter selection for accurate and efficient condition monitoring. Machine vibration analysis in practice. Consider a case where a centrifugal pump exhibited elevated vibration levels. Initial analysis with incorrect Fmax settings failed to reveal bearing fault frequencies. After adjusting Fmax and increasing resolution, the spectrum clearly showed bearing defect harmonics, enabling timely maintenance and preventing catastrophic failure. Another example involves a gearbox where spectral averaging helped distinguish gear mesh frequencies from background noise, leading to accurate diagnosis of gear wear. These cases highlight the importance of proper parameter selection and advanced techniques in real-world scenarios. They demonstrate how theoretical concepts translate into practical solutions, reinforcing the value of skilled vibration analysis in industrial maintenance programs. Summary: best practices and key takeaways. Effective vibration analysis relies on a solid understanding of signal processing fundamentals, analyzer functionality, and parameter selection. Key best practices include setting appropriate Fmax and resolution, applying spectral averaging judiciously, and leveraging analyzer features for accurate diagnostics. Analysts should continuously refine their skills through training and practical experience, ensuring they can adapt to diverse machinery and operating conditions. By following these guidelines, organizations can enhance reliability, reduce downtime, and achieve significant cost savings through predictive maintenance strategies.